Hello, this is Ms. DB, and in this video we are going to review how to do Chapter 7, Section 1 on exponential functions, growth, and decay. Our objectives for this lesson are to write and evaluate exponential expressions, to model growth and decay situations. We will use technology to graph these. All right, if you double an amount every year, you can call that, you can model that using a function that has a variable as an exponent. Now, we've used exponents before, but our exponents have been numbers, real numbers, not variables. So now we're looking at something called exponential functions, where there is a base, which is a number, a constant, and the exponent is the variable. So that's what's different. Our base will always be a number greater than 0, but not 1, because 1 to any number is just 1, because 1 times 1 times 1 times 1 is always equal to 1. Also, there might be a number in front of your exponential function, a, so it might be a times b to the x, often will be, and a is a constant and b is also a constant. And again, the base will it'll always be greater than 0. If it's between 0 and 1, that is, if it's a decimal number, your function will show decay. If your function is greater than 1, your function will show growth. And our variable is the exponent, so that's what's different. Here's an example of a graph of an exponential function. This is the graph of f of x equals 2 of x, 2 to the x power, sorry. So if we took 2 to the x power and graphed it, we would get this graph here. You could find that by using technology or by plotting points. If you take 2 to the negative 2, that would be the same as 1 over 4. If you took 2 to the negative 1, you would get 1/2. 2 to the 0 is 1. Anything to the 0 power is 1. 2 to the 1 power, of course, is 2. 2 to the second power is 4. 2 to the third power is 8. And if you plotted those points, you would get this curve here. The domain of this exponential function is all real numbers. There's nothing that x could not be. So we'd say all real numbers. The range, however, never will be negative. The y value will never be negative, the value of this function. So we would say that the range is y is greater than 0, or all positive numbers. As the x values decrease over here on the left side, our function is getting closer and closer to the x value. Very, very close, but it never will touch it because it can never be 0. 2 to the x can never be 0. So we call the x-axis an asymptote. An asymptote is a line that a graphed function approaches as the value of x gets very small, like we see over here on the left, or sometimes very large. So it'll get closer and closer to the line, well, in this case, it is the x-axis, or the line y equals 0, the more that the x value decreases. There is no asymptote as x increases because it's going to keep growing and growing and growing. It'll grow quickly, but there won't necessarily be a limit to that. A function of the form f of x equals a times b to the x, with a greater than 0 and b greater than 1, is an exponential growth function. We talked about this already, which increases as x increases. When b is between 0 and 1, that is greater than 0 and less than 1, the function is called an exponential decay function, which decreases as x increases. Those are the two different models that we're going to be looking at in this section. In the function y equals b to the x, y is a function of x because y depends on the value of x. So that means it's a function of x. And also remember that negative exponents indicate a reciprocal, and we already looked at this when we had 2 to the negative 2, we wrote 1 over 2 squared, or 1 over 4. So x to the negative 2 equals 1 over x squared. All right, so continuing on, we've got lots of background information. Now it's time to look at some problems. First of all, we're going to just tell whether or not this function shows growth or decay and then we'll graph. So we're going to try to decide before we look at the graph whether it's exponential growth or decay. And here's a little review information. If b, the base, is between 0 and 1, then it shows decay. If it's greater than 1, it shows growth. So over here, we need to figure out what is a, what is b, so that we can tell what the base is. Well, a is the number in front. This is a right here. So a equals 10 in this problem. B is the base. That's the number that we need to look at and decide whether it shows decay or growth. So is b 3/4 greater than 1? No, it's between 0 and 1. So this function shows a decay. So we found the base, and the base is decay. Now the next thing to do is to graph this. When we graph this, we can graph by hand. Let me just go back and look at the problem again. It was 10 times 3/4 to the x. 10 times 3/4. And if you wanted that to be a decimal, 0.75 to the x, there's no problem rewriting it if you prefer decimal form. So one way to graph this is to plug in values for x and solve using a calculator and find out what you get. Do be careful that when you use a calculator that you do the 3/4 to the power and then multiply by 10. So you have to take in the first one, 0 is easy because 3/4 is 0 power is 1, 10 times 1 is 10. For the second one, you would take 3/4 to the second power and then multiply that answer by 10. So 3/4 to the second power is the same as 9/16, and 10 times 9/16 simplifies to 5.6. So make sure that you are raising the base to the exponent before you multiply by the constant in front. That's very important. So here's the values all calculated out for us. And then after that, you would plot the points. I'll erase this out of the way here. On a graph, and then connect them with a smooth curve. So at 0, we're at 10. At 2, we're at 5.6. Now you're going to have to estimate when you graph exponential functions. You're going to get lots of decimal numbers. And so on, you would continue plotting the points and then connect them with the smooth curve. Another way to graph these is with technology, and we'll look at that in a minute. Okay, here's another example. You have to say whether it tells growth or decay and then graph. So in this case, A would be 100. That's the constant right in front. B is the one that's being raised to the exponent. And B, remember, is the one that you have to look at in order to tell if it's decay or growth. In this case, since 1.05 is greater than 1, this is an exponential growth function. You can graph, again, using a table, or you could use a graphing calculator. This is like an example from like a TI-84 or TI-85, whatever you have for a graphing calculator. And it would look like this. You can graph it just by typing in the function 100 times 1.05 to the x power. Make sure you use parentheses in order to make sure that this is the part being raised to the x power. If you have a graphing calculator, yours should look very similar to this. Whoops. And then that was all you had to do for this problem, was graph it. Okay, on your worksheet, you have to show me your graph. So here's number 1 from the worksheet, and here's the problem, 0.8 times 1.6 to the x. So first you need to tell whether it shows growth or decay. A is 0.8, B is 1.6, and B is the part that we are concerned about that we check to tell whether it has growth or decay. Since 1.6 is greater than 1, this is exponential growth. Okay, next for graphing. You can graph it by hand. So you would just plug in some values of x, and then you would solve in order to find the value of the function. I just have to grab my calculator tool here so I can show you what I get for values, because I don't want to do these in my head. Okay, so first, here's what you would put in your calculator. You would put in the 1.6 to the -6 and then multiply by 0.8. So 1.6 to the exponent -6, and where's my negative key here? 6 negative, and then hit equals, and then multiply that by 0.8. Okay, I get 0.0476, so I'm going to round that to 0.048. Let's see if I can get that in there. 0.048. Okay, then I got to get my calculator back for the next one. Clear this out. Next one would be 1.6 to the power of -4. Hit equals, multiply that by 0.8. And I get 0.122. Now when I graph these, I'm going to definitely have to estimate because these are very small decimal values. And you would continue this, 1.6 to the -2 power, hit equals, and then multiply by the 0.8, the constant in front. And I get 0.3125. This is growing, but it's growing very slowly compared to our other ones. At 0, I can do this one in my head. Anything to the 0 power is 1. So I just need 1.6 times 0.8. Well, maybe I'll check that. 1.6 times 0.8 equals 1.28. And now it's starting to grow a little bit faster. You'll see with exponential functions, either growth or decay, they increase or decrease quite rapidly. And this is to the 2nd power times 0.8, 2.048, and then 4. When x is 4, I would have to the 4th power times 0.8. The multiplying by a number less than 1, the 0.8, also is keeping it from growing too quickly. And then I'll do one more and see what we get. So 1.6 to the 6th power times 0.8. 13.42. Okay, now we will graph these by hand. I'm going to go back to the slideshow so I can use my pen. And here's my values. So at -6, which is about here, we're only at just barely above the x-axis. There we go. At -4, we're still very low, just slightly above that at 0.122. At -2, we're still not even at halfway. And at 0, we're finally above 1, 1.28. At 2, we are at 2.04, so just almost on that point there. At 4, we are at 5.24, about 5 1/4. And at 6, finally we see a good amount of growth here. We're almost at 13.5, so right at 13.4 is right about there. And then you are to connect this, if you're doing this by hand, with as smooth of a curve as you can. I'm using a attached notepad here. It's a little difficult, but you would try to make it smoother than that. Now, as you can imagine, it would be much easier if we could use some technology here. So let's graph this 0.8 times 1.6 to the x with Sketchpad. Let's move this over so you can see it better. So we are going to graph, go to graph, plot new function, and the function was 0.8 times, or you can use the parentheses, 1.6 to the x power. So this button right here tells you to use an exponent, and then you just click OK, and it's graphed for you. You can use these buttons over here to move down or up to see what's going on. You can move this around and put it right next to the graph, and then you need to take a screenshot of this, a picture of this, or attach the file in order to show your work for the assignment. There'll be another problem that you're going to do, so you can go to File, and it's going to be cut off a little bit for you, but go to Document Options and then go to Add Page to get a second page of the same file if you want to attach your graphs when you're done. And then you can make the next one right here. Okay, going back to our slideshow, we could also use Desmos.com to graph this. I'll show you what that's going to look like. Okay, so our Desmos.com calculator is an online graphing calculator. Let me resize it so you can see the whole thing. Over here is where you'll enter your function, and the function was, again, 0.8 times 1.6. Now I need the exponent button, which is looks like this on Desmos, and then the x, the variable x, and it graphs it very quickly for you. You can't save graphs on Desmos, but again, you can take a screenshot and then attach your screenshot to the worksheet in order to show me that you graph this. So real quickly, we can see that this is exponential growth. You can zoom out to see more of your graph, or you can zoom in to see more specific parts of your graph. You can drag it around as well. Okay, back to our problems here in our slideshow. All right, a little bit more information here about growth and decay. When we have a percent increase or decrease, there's a slightly revised formula for us, and you'll see a lot of word problems that have a percent increase or decrease. Then your formula will be 1 plus r, where r is the percent increase or the percent increase as a decimal, or 1 minus r if it's a decrease. R has to be a decimal. I'm going to write that down. Percent written as decimal. So a quick review, if you had 50%, you would write that as 0.5. You move over 1, 2 places. 5% would be written as 0.05. Our percents will usually be quite low, so you will often have a 0.0 and then the number. T is the number of time periods. So if it's exponential growth, it'll be 1 plus r. If it's exponential decay, it'll be 1 minus r. And instead of t, it's t in the formula, but we'll use x in our graphing technology. There's not generally a t as a variable option. All right, let's look at this example. First, you have to decide whether it's exponential growth or decay, so you can use the right, whether it's a plus r or a minus r. Clara invests $5,000 in an account that pays 6.25% interest per year. After how many years will her investment be worth $10,000? So she went from $5,000 to $10,000, so it's increasing. So first thing is to write the model, the function, by replacing the a and the r, and sometimes you can replace the t, but usually with the t will stay there because the question is saying after how many years. We're looking for t. So we'll replace the a with the initial value, and the initial value is 5,000. So a is equal to 5,000, that's the initial value, and r is 6.25 written as a decimal. So 6.25, move your decimal point over 2 places. You have to add the 0 after the decimal. So that's part of it, is to write the function that models that. And then we can simplify that just a little bit by adding the 1 plus the 0.0625 to get 1.0625 to the t power, and then the 5,000 in front of that. Now, if we want to graph that, we'll be able to find out the answer to the question. The question says, after how many years will her investment be worth $10,000? Well, it's hard to tell. It's hard to solve this, but what they're really saying is, when will this be equal to 10,000? They're saying, what is t? Oops, I missed a 2 there. What is t so that this function would be equal to 10,000? The easiest way to find this is by graphing the function. And then we can look and see, when does it equal 10,000? So here's the graph on a graphing calculator. not the clearest graph at all. But the graphing calculator has a trace function so that you can find where is it equal to 10,000. And you just keep hitting your little trace button, your little arrow buttons until you get there. And then you can use that trace value, and you can even get a table of values to find that it looks like it's between 11 and 12. So you might estimate 11.75 years, or you can just say it's about 12 years. Now we're going to look at how we will use graphing technology to do this problem. Now here's number 3 from your worksheet. It says that an initial amount of $40,000 increases by 8% per year. In how many years will the amount reach 60,000? So it's very similar to the last example. It's exponential increasing. Our initial value is 40,000. Our R value, remember we have to use a decimal, so it's 0.08. Now the next question to figure out is C, which is what is the function? What is our model? We have to replace A and R with our values that we just found in A and B. So 40,000 is A and 0.08 is R, so we write it like that, and then we can simplify that a little bit by just adding the 1 and the 0.08 to get 1.08. Now we're ready to graph. Let's graph at, you can use either one to graph, but I'm going to graph at Desmos. So this time my function is going to be 40,000. Oops, I don't need that decimal there. 40,000, one more zero, nope, too many zeros, times 1.08. And I'm going to use x for t because they don't really have a t variable sitting here. Put the comma in there just to make sure. Yep, that's 40,000. Okay. They don't like the comma in there, so I'll take it away, but I just wanted to make sure I had the right number of zeros. Now, nothing's showing up in my graph over here. The reason is that this graph is way over here. Why is it negative? Okay, the reason that it's showing up so strangely is because at the initial amount, it's already at $40,000. It's already way up here. So it started out way over here at negative, and then it increases really rapidly. So I'm going to fix the way my graph looks by going to graph settings. Right now, my x-axis is showing from negative 5,000 something all the way to 5,000 positive. I'm going to change this so that it's only showing from, oh, let's say maybe negative 24, or I'll say negative 20. And then I want to go up to pretty high because this is going to increase a lot. So like 200,000. Oh, no, this is my x value. My x value only has to go up to like positive 20. And my y value is the one that I can start this at 0 because it's never going to be less than 0. And my y needs to go up quite high because it's starting at 40,000. It's going to grow, so it's going to go quite high. Should we go one more zero? Is that too many zeros? All right, let's see what this looks like. And we can adjust as needed. All right, so now we can see that there's my negative values, which I don't really need to worry about because I don't have negative years. I'm really starting here at 0. When I first put the money in, it's at 40,000. One of the nice things about Desmos is that you can click and you can get values of points. So there's my starting value right there. Now my problem asked me to find when is f of t going to be equal to 60,000? 60,000, okay. So I need to go back to Desmos. If I can find it here. And here's 60,000 would be up here. So let's see, here's 60,000 right here. So if I click on the graph, That's a little lower, you can make it go right where you want it, as close as you can get it. You might not be able to get it exactly, but that's okay. So here's pretty close. Ooh, I hit it at 60 there. And I'll double click to get that point to lock in. Won't it lock in? It won't. How about this point? Will this point lock in? Well, it won't lock for me right now, but I can see that at about 5.3 years, it's at over 60,000, so it must be just under 5.3 years. So maybe 5.2, 5.3, right around there. So now I am ready to fill in that it is at approximately, whoops, t is at about 5.3 years. And I use my graph to find that. That's a different problem. Okay, here's another example. A city population which was initially 15,500 has been dropping 3% a year. So write an exponential function and graph the function. Now this time, and now they want to know when is it going to drop below 8,000. This time it's an exponential decay. So you fill in your values, but this time you use the model 1 minus r. And when you simplify, you'll get 0.97. You'll get a value less than 1. This is a graph on the graphing calculator again, and to find when it falls below 800 looks like around 22 years. But you can use Geometry Sketchpad or Desmos in order to graph. Here's just the last couple problems on the worksheet. I just wanted to help you set these up a little bit. A quantity of insulin used to regulate sugar in the bloodstream breaks down by about 5% each minute. A body weight adjusted dose is generally 10 units. Write a function representing the amount of the dose that remains. So our function of time is going to be equal to the amount that you start with, which they said was generally 10 units. Now is this decreasing or increasing? It's breaking down, so it's going to be decreasing. And it's decreasing by 5%, which we need to change to a decimal, like this. So here's your function. And then for b, you are going to graph this using Desmos or Geometry Sketchpad. You don't have to attach your graph for these, so use whichever ones you like better. And then you are going to graph it, and then you're going to answer the questions about how much insulin remains after 10 minutes, about how long does it take for half of the dose to remain. So that would be about 5, so equal to about 5. So let's see, if we look at our graph, 10, oh here, you should simplify this. This would be 10 times whatever 1 minus 0.05. Let's use Sketchpad this time. Because then I can move it around a little bit better and see the equation. It was 10 times, well, I was going to have you do that part, but that's okay. And it was to the x power because we don't have a t as a variable. So do I have my equation correct? Yep. Okay, and again, you can't really see this. So in Sketchpad, to zoom out, you can click on that dot and drag. And then you can click on the end of that arrow and continue it, because it stopped because that was all that was showing on our graph. So we have this graph here. So question C said, about how much insulin remains after 10 minutes? Well, that's when x, or t, is equal to 10. So that's right here. You could even put a point, grab the point tool, and put a point at 10 and the intersection of the graph there. And then you could go to measure the coordinates of that point. It's just slightly over 10. Maybe I can move it a little bit. At 10, it looks like it's right about 6, just about 6. So for how much insulin remains after 10 minutes, it's about 6 units, I guess you'd call it. And then the next question says, about how long does it take for half the dose to remain? And I said that was about 5, when your y value, your function value, is at about 5. So that looks about right here. And again, you could grab the point tool and you could put it at about, right about 5. And you can measure the coordinates. And you could see, it's not quite 5, but it's right about. So it looks like about 13.6 minutes is when you have about half the dose remaining. So Sketchpad is a good tool too. So use one of those in order to do number 7 as well. And this one, it says self-employed people can depreciate the value of business equipment. So that's a good clue that we're going to be using depreciation here at a rate of 30% per year. And the R value is not 0.03. This time it's actually 0.3, I mean, sorry, not 0.03, but just 0.3. And then we're going to estimate the number of years it will take for the computer's value to be less than 350. So when on the y-axis you're at less than 350. Find what x is equal to. All right, well, let me know if you have any questions. Thank you very much and have a wonderful day.